Hello there. Today I want to talk about another debugging story. This time about how I went about fixing a race condition in a parallel hash map, log-free hash map for dots, so for Unity's data-oriented tech stack. So we have our own collections library, of course, like everybody does, and that's where this race condition came up. So first, how did we get here? So basically, we had a client, and the client was reporting data corruption in the dots transforms package. So we have a transform hierarchy, transform stack, and at some point there we are updating parents, like the parenting relationships, and you have to update child pointers, and that's going through various contortions, and at some point you're using a hash map, and when you read from that hash map after something was collected, be garbage data in there. Not just garbage, but also garbage. And it's a relatively infrequently appearing problem. Happens about once or twice every 2 million frames, if I did the math right. I already did the math wrong on this once, so it could be that this math is also wrong. But essentially, when it would happen is you have 16 players in your game over a 2-hour play session. They're running at like maybe 40 FPS at the time of speaking. And that kind of comes out to once in 2 million frames when you have one crash in there. So essentially, those 60 players would play, and in the background, they'd play Russian roulette as to who gets to crash first. So the first thing that we want to do, or that we had, the first lead is one of our friends from that developer, Sam, they collected some crucial clues. So when the hash map, or when the hash map had that problem, when the game crashed, we knew exactly what the state of the hash map was. And by that I thought, oh, I know how to do that. I'm going to write a stress test. And this is going to completely just show where the problem is. So I had my stress test written where I have 16 threads operating on that single parallel hash map, just trying to add stuff to the hash map, and did that for minutes. Nothing happened, and I thought like, that cannot quite be right, because once in 2 million runs, you get to 2 million runs fairly quickly if you're doing nothing but instantiating, creating a hash map and then writing to it a few thousand times and then doing the same thing again. But nothing happened. So the first lesson here is, if something happens that rarely, it's probably not just because it's a data race. There are some specific conditions that make this data race happen, and we need to recreate those specific conditions. And to me, the first natural thing to do was to look at the code paths that actually exist. Now, I didn't write that parallel hash map, so I didn't know what to look at. So it took just some experimenting. But I knew what the corruption looked like, thanks to the data that we already had. And at the core of our multi-threaded hash map, there's something like this. I think in the code it's called alloc entry and free entry. And it doesn't quite look like this, but this is the gist. So when you get a key to insert, you have to find out which slot to insert that key in. And in the parallel case, for the parallel hash map, the capacity of the hash map is fixed. So there's a fixed number of slots, and they live in a shared pool. And whenever you need something, you need to allocate an element, a slot, you go to that shared pool. But because if all of the threads always contend over that shared pool, that's going to slow them down. So instead, every thread also has a local cache. So it doesn't have to go to the shared pool for every slot, but it can go to the shared pool and fetch an entire cache line, where cache line here means 16 entries, but it's not so much contiguous memory, but it's more like a linked list of entries. But it doesn't need to go to the shared stash for every, or shared pool for everything, but only for every 16th, because that's these 16 values cached up. So it tries to get it from its own cache, the index. If it fails, it has to refill their own cache. So might be that you're depleting your own cache and then you try to get some more from the shared pool. But that might also fail because the shared pool is finite and we can't resize, or that's at least not what this hash map was optimized for, or made for rather, like it just doesn't support it. In this case, it doesn't mean that we don't have any indices left, because it could also be that another thread still has indices in its cache. So then we need to steal from that thread's cache. And then I guess technically you also need to handle the case if that failed, because that means you're actually out of indices. Almost. There's like an edge case how you could also make that fail, and let's not think about that for the moment. Then when you've acquired the index, then you add your entry. But then comes a little bit of an interesting next step. You have to actually check whether somebody else added the same key while you were doing all of this dance. And if they did, you have to return your slot index to your own cache. So there's like these caches that you read and write from, and you return things to them and you steal from them. So it's not exactly an easy setup. And originally this part with the returning the slot index didn't even exist, because apparently this case just wasn't happening enough that somebody thought about it. And at some point people realized, hey, there's also this race condition. What if two threads try to add the same key? And then they said, okay, in this case we have to check and we have to return the slot index to its own cache and rewind some work. Okay. Now, I was fairly confident that all of these code paths were executing for my stress test. Being fairly confident is not the same thing as knowing. So the next thing to learn is you should actually prove that you're testing the thing that you actually need to test. So in my case, what I ended up doing is I added atomic counters to each of these code paths to just see which of them would execute. And it was very clear that the refilling was happening all over the place, the returning was happening all over the place, and I thought, oh, that's the unlikely case that something's going to return. But the stealing was just never happening. And I didn't know why. But if you think about it, it's actually quite understandable why the stealing would never happen. The stealing only happens when you operate close to capacity, when the hash map is close to its capacity. Now, the size of the cache is 16. In the case where you're operating close to capacity, what I mean is the cache, all data is in caches and nothing else is in the shared pool. But you can, if you have 16 threads, that means your hash map can at most have size 256, because otherwise not all of the indices can be in caches. So it naturally limits the size of the hash map that you can actually consider. But if you take a very small hash map, a naively written stress test is probably going to scale in the size of the hash map. So you're just making it unlikely that you're going to hit that case, because you need to have a small hash map that you write to in parallel. And it just seems like if it's worth multi-threading something, it's probably because you work on scale. This, incidentally, also proves, or not proves, but explains why this crash was happening in the parenting system. Because in the parenting system, what we deal with is a hierarchy of things. And what we do is we collect paths, we collect parents in that. And there's only like the number of parents is just much smaller than the number of actual paths that we could consider. Particularly because we usually have pretty broad hierarchies in this case. So that's why it was happening in that case, because it hit the exact conditions. Small hash set, but still there's enough work that many threads would have to operate on that small hash set, and that small hash set is actually pushed to its capacity. Because in that parenting system, we very explicitly calculate what's the maximum number that we could ever get here. And that's why it's only happening in that case. So how would I write a stress test for that is my next thought. And it occurred to me that I don't have to write a stress test with these parameters. I can actually change the odds in my favor. And that's the next lesson. If you can, do that. The question was, how do I get the stealing to actually happen? And that means that the refilling had to fail. When does the refilling fail? Well, when there's nothing in the shared pool, or in other words, everything is in the caches. So ideally, only one thread would have a cache and all others would steal. Then all of this time we would steal. Okay, we'd sometimes also return things to our own cache, and then we wouldn't have to steal for a while, but ideally we just want one thread to have all of the data. So the solution was simple. Change the hash maps implementation to use a larger cache. I bumped the size of the cache to essentially be the size of the hash map, and immediately the error would appear. What's also interesting is, because I added this logging before, like with the atomic counters, I could now test what happens if I only have the stealing running. You could like of these of the lower two cases at least. Like the refilling will always have to happen somewhere, but I already know that if the stealing doesn't happen, then I don't get a race condition. I could now also ask, like, what if the stealing happens but the returning never happens? And I did that by just not writing the same value from different threads. And it turns out that then the race condition is also gone. So the only way that you get that race condition is if you have both the stealing happen and the returning happening. So let's look at the two pieces of code. And I'm going to show you the returning code at the top, because I think it's actually the more understandable one. They're quite understandable both. So what you're looking at here, up there, is the returning code. And down here, this is the other code, the code for stealing. It's very similar to the code for just taking from your own cache, but let's just take one of them. So the way that this cache is implemented is through a free list. And in this free list, every element has a pointer to the next element. So what we do is we look into the first tree, which is essentially the head of the list, and the TLS here is thread local storage, because for every thread we have their own free index, and then we multiply it by ins per cache line to prevent false sharing and blah, 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 blah. Not relevant. So we read the next thing that we could get, and then because we are trying to return our current index into the first free slot via compare exchange. Like, if you're not familiar with how that works, and I'm unfortunately not going to explain how a compare exchange loop works for atomic operations, because that's just taking us too far for a video that's aimed at 15 minutes, and we're already 13 minutes in. What we're doing is we're returning that index, and before we return that index, we write to this next pointer. We're writing, saying, hey, the thing that was in the list before in the beginning, that's now the next thing for the thing we're now adding in the front of the list. So we are pushing things on the front of the list. The way that I think about it is, as long as this interlocked compare exchange hasn't happened, the index is still owned by the current thread. So as long as we own the index, we can write to this next pointer at position index. Now the stealing looks like this, and congratulations if you already figured out where the problem is, because I stared at this for 2 days, but I guess the 2 days included trying to do all of this stress testing and all of the different things, and I didn't immediately see it. So what we're doing here is we take the index, and then we try to do a compare exchange with the next item. So we pop the first element from the list, and we exchange it for the next item. And this is actually where the race condition is. This code is not correct, because if you rewrite that code briefly, it looks like this. And the way that, again, I want to think about this interlocked compare exchange is, before that interlocked compare exchange has happened, the thread that we're currently on does not own the index. So another thread could own the index, and we know from the returning path, if something else owns the index, they could write to the next element. They could update what the next element is. So the race is that somebody could be executing this code here and then return it, while you in between read this one and then try to take it. So this next that you could have read is stale, and then you have created an invalid cache and will look like you have dropped entries. The fix is rather simple. What you do is like you add another exchange in between, you add a sentinel value or something, but that's not really all that interesting. But the lesson to me here is any memory access in an intellect exchange is cause for suspicion. And now for the fun part. I told you about the previous change like 2 years ago, where somebody realized there's a race condition if I add two things, and they added like this lower returning. This race condition was also because there was a memory access within the intellect compare exchange, and really within the intellect compare exchange, I mean within the statement. It's not actually within it. That's a problem. If it was within it and also atomically part of that, it wouldn't be a problem. It just syntactically is in there. It was the same kind of problem, but a little bit different. But only this returning introduced this problem, because before the returning code existed, this code down here, the stealing code, was completely fine because nobody would ever give ownership back. That wouldn't happen. So we didn't have to care about the case, what if somebody else already owned this, made a change, and then gave ownership back? And this code wasn't changed. So a change somewhere else introduced this race condition. And yeah. Now for the last lesson, and probably the most important one. There would have been a shortcut to cut this 2.5 days of effort short. This is my colleague, Adam. Adam said on day one of looking at this thing of our 2.5 day exploration, this next pointers index in the compare exchange looks really suspicious. I think just my brain wasn't there yet. It took me 2.5 more days than writing a stress test. And I think at least I came up with a explanation for why it actually is wrong or not just suspicious. But really the lesson here is listen to Adam. It's going to save you a lot of time. And if you don't have this kind of Adam around, like I'm very sorry. We're not giving him away. So here are my lessons that I learned. I hope this was interesting to listen to. And yeah, thank you very much for staying with me. I hope this was interesting. Bye. See you next time.